Okay, so today we will continue with our study of chaotic systems and return to the Duffing oscillator, where we will see something quite powerful. So let us think of this as the unperturbed part and think of a small damping and a small forcing. We have seen for a finite amount of damping and forcing that there is chaotic dynamics in this system. We have seen a positive Lyapunov exponent. We have seen very complex trajectories. We have seen a sort of stretching and folding of points on the Poincare section as we have moved the Poincare section along from 0 to 2 pi in phase. But now we will take a different approach and try to understand what happens when epsilon is small. Okay, so first consider epsilon equals 0. Then only this part is 0. Very good. And what that means is we have a phase portrait that looks like this: x here, x dot here, one equilibrium here, one here. This is unstable, one stable, one stable, and unstable direction, a stable direction. This is a hyperbolic fixed point, right? And then this is a center, and this is, therefore there are periodic orbits like this. This is another center. If you are confused about the direction of the arrow, remember that when x dot is positive, x has to be increasing, so the arrow has to be like this. There is one special orbit like this which we have seen earlier called a homoclinic orbit. There is another homoclinic orbit here. If we have bigger amplitude motions, then they are like this. What is hyperbolic? This fixed point is hyperbolic. Okay. Now, what happens with epsilon greater than 0 but small? That is an interesting question. Now we will also simultaneously think of this system using Poincare maps. Okay, so when we think of this as Poincare maps, what we are thinking of is the picture we have seen before in earlier lectures, you know. So maybe x dot and t, but we go from 0 to this distance is 2 pi over omega, and once again we have another x dot and another x. There's a plane here, there's a plane here. These two planes are essentially the same because it is periodically forced. You take an initial condition here, it reaches this place, you shove it back here, it reaches this place, you project it back here, it reaches this place, and so on. So this mapping is the Poincare map, right? So where are we now? This. So this is the map. Okay, let's go back here. When epsilon is absolutely tiny, in that case, that evolving point, the one that goes from here to here, but is then drawn, projected back here, so that point that moves from here to here, this movement of the point is actually a jump. It is not a flow, but this point may jump here, and this point may jump here, and this point may jump here, and the gaps will slowly increase because this is the unstable manifold. This point would jump here, and 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 so on. And then over here, if there was a point here, let me use a different color, let me use green. If there was a point here, it would jump here, and then the gaps would be slowly decreasing because this is the stable manifold. Okay, so of course there is another minor matter, which is that because this is a hyperbolic fixed point, so the Poincare map is robust here, in this area. So what will happen is, if we take epsilon greater than 0 but small, then in the same Poincare map what will happen is that maybe this fixed point will be perturbed by some small amount, but the fixed point will survive. Because it is hyperbolic, you can do numerical root finding and see that you will find there is such a fixed point. In any case, because it is hyperbolic, it will be robust, the structure of the map will be robust, and so there will still be an unstable direction, a stable direction, right? And over here, I will still have a point that gets mapped here, and in this way it proceeds. Points over here will get mapped in this direction and proceed. But remember, they are not flowing along the curve. It is, even if there is a curve like that, the point is hopping. It is like a divider which is being used to take discrete steps along the curve. There is an underlying curve and we are taking steps along the curve. This is really important. Why are we taking steps? Why are we not moving continuously along the curve? That is because we now have a Poincare map, right? So this is really important. You will find this in various books. It is discussed. You need to get comfortable with this idea. Okay, so once you are comfortable with this idea, you reach this wonderful conclusion. And the conclusion is that somewhere over here there is still a fixed point. Somewhere like this there is still an unstable manifold of the map. And somewhere over here are points, so this point gets mapped here, this point gets mapped here, this point gets mapped here. However, this point gets mapped here, this point gets mapped here, this one gets mapped here. It doesn't pass through the green point. Okay, and in this way, when you take the map, if you compute it numerically or computationally, you linearize it, you can find its eigenvectors, and in this way you will find the unstable direction. So let's call this the unstable direction. Now similarly, there is going to be a stable direction which will come from somewhere like this. This is the stable direction, and on this stable direction you could have a sequence of iterated points that are coming like this, getting closer and closer and closer, and you could have a different set of iterated points like this. This one gets mapped here, this one gets mapped here, this one gets mapped here, and so on. This blue point does not pass through the green point. It is hopping along. It's like using a divider. In the geometry box from your high school, you had these dividers. It's like that. You're taking steps with a divider. Okay, so this is how the mapping is working. And then the big question comes is, what happens if you extend this curve? So here is one possibility. This curve goes like that, and this you extend backwards in time because it's an ordinary differential equation underlying, so you can solve it backwards in time. So in principle you can run this. So here is one possibility where they split but they don't intersect. Here is one possibility where they don't split at all. But here is another possibility, which is that they intersect transversely. And this is the most fascinating case, and this is the one we will look at now. Okay, so here we are. Now we are considering this situation where there is some fixed point. Now you will agree it doesn't matter if I just draw it here. This is the unstable manifold of the Poincare map, and this is the stable manifold of the Poincare map. And for some reason they have intersected here. If this was a flow, you could not have that, right? Because you cannot have going like this and going like this from the same point, because it's a flow. You cannot depart in two directions. But remember, this curve is generated by hops. Okay, so you have reached here. If you follow this curve backwards, you are only interested in the next hop, and that next hop, you are following this backwards, it must intersect again. Okay, because you're tracking this backwards. So this point, the point just goes where it goes, right? The point goes from some place to some place. If you think it is on this curve, or you think it is on this curve, that is your business. You are thinking about it. So now this point is on this curve. Therefore, in its previous iterate, it must have been on this curve, right? And this point is going along this curve also. So in its previous iterate, it must have been on this curve. That means these curves intersected again, and that means they will intersect again, and over here they will intersect again, and over here they will intersect again. And let me just draw this part. So you will just have infinitely many intersections, and you'll get a complete tangle over here. This is called a homoclinic tangle. The name associated with this theorem is actually two, so there is three. So there is Poincare in the background, and then Smale, and then Birkhoff. And the key thing that we are interested in is that if there is any intersection, there are in fact infinitely many intersections. That's the first thing we are interested in. But even if there is one intersection, something really interesting happens, and that is where I will wrap up my discussion of chaos, is like this. So let us say this is the unstable direction. This is the stable direction. And these have intersected somewhere. Okay. Now let us consider a little blob of initial conditions. Iterate forward many times, then this blob will shrink in this direction and extend itself in this direction, so that it looks like this: narrow and long. Sorry, like that. But on the other hand, instead of forward iteration, if we do backward iteration, if we iterate backwards, then this same blob will extend in this direction and in that direction, because we are iterating backwards. And it will meanwhile shrink in this direction. Okay, and so now there is some finite number of backward iterations which will take you to this situation, and then from there a finite number of forward iterations will bring you to the blue, and then another finite number of forward iterations will take you to this red. And so there is a finite number of iterations that will take you from this green to this red, and I hope you now recognize the topology of this. It does not look like it has straight edges, but this is basically the horseshoe map. This is rather remarkable. And so what it means is that if there is a transverse intersection of the stable and unstable manifolds of a hyperbolic fixed point on the Poincare map, in that case, hidden in that, there is a horseshoe map. Because there is a horseshoe map, there is an invariant set of trajectories with all those nice things, complicated trajectories, exponential separation of nearby trajectories, fractal nature, and so on. And so you have chaotic dynamics possible, but not guaranteed, because we have not shown that it is attractor. It is an attractor. That is admitted. But numerics have shown that there is an attractor. So I think that this is a nice theoretical contribution. Of course, the study of dynamical systems is very advanced and complicated, and many people have studied many things, but I will stop here. I will only mention one last thing. For systems like this, for wherever we were, let's see now. For systems like this, there is in fact a perturbation calculation that can be done to find a condition such that such transverse intersections will exist, and that calculation is associated with the name Melnikov. That's Melnikov's method. Using that, you can find, for epsilon going to 0 plus, you can find conditions such that such intersections will occur. But of course, you still don't prove the existence of a chaotic attractor, and Melnikov's method is something that I no longer cover in my course. And so the chaos part of my nonlinear vibrations course is now over. If time permits, I sometimes discuss delay differential equations, which is a completely different topic, and so this is a good stopping point for the course. Thank you for your attention.